All right, so we did a little bit of algebra at the beginning to get this expression for beta hat 1. You remember, it equals the true value plus this term. Right, and then how we that's right before we took the expectations of both sides and kind of, using our assumption, got rid of this second term. But now we're going to use this expression for beta hat 1 to calculate the variance of beta hat 1. So we just need to take the variance of both sides, and again, we can use the fact that the true value is a constant, some number. So right now we're just taking the variance of both sides. Let's get green out. So again, beta 1 is the true value. Of the parameter. It's not a random variable. And in the same respect, maybe I'll just do it all at once, x1i is not random after we draw the sample, once we draw the sample. So beta 1 is not a random variable because it's just the true value of this parameter, and x1i, once we actually draw the sample, I mean, it's not a random variable. Before we draw the sample, it is, right? And so what we're left with, let's get rid of the first term, the variance of the sum of x1i. So I guess we're just kind of using that first thing that I wrote out now, just to divide it up into a couple steps. And so if these, if this, in this denominator, if this x1i minus x1 bar, if these aren't random variables, if we've already drawn the sample, then this denominator is like a constant, right? And so we want to take this constant outside of this variance. Well, to do that, we need to square it, right? Remember, if you're multiplying or dividing a variance by a constant, we take it out of that variance, we need to square it. So that's what we're going to do. And that's kind of, I guess, this part of it. I don't know what I was trying to draw there, right there. So here we're using this to get rid of the beta 1, we're using this first thing, and now we're going to use this second idea, this idea that x1i is not random. So as we were just seeing, we have the variance of beta hat 1. So we use that first green line there to get rid of that beta, the true value of that beta 1, and then we're going to use the second kind of line, that green line in the last board, I guess, to kind of bring out that denominator and square it, right? So now we're going to have 1 over x1i minus x1 bar squared, and we're going to square that whole thing because we're bringing it outside of this variance. We still have this part of it kicking around. Yeah, you gotta take the variance still. We still have this part of it kicking around. We can't get rid of this x1i minus x1 bar now because it's part of this sum and we're multiplying it by ui every time. So now we have to think about making another assumption about this relationship between x and u. So that's what we're going to think about now. So we need to make another assumption about the relationship, about the error term again. I don't think I need again because I said we need to make another one. Okay, And so the assumption we're going to make, maybe I'll just put a colon there. The assumption we're going to make is that the variance of u conditional on x1, so the variance of our error term conditional on our independent variable, is constant. So what does this mean? The variance of u is the same no matter what the value of x is. So the variance of u doesn't depend on the level of x. And we're going to call this homoscedasticity. And that might be really hard to understand what this assumption's saying. So let's just explore this assumption for a couple minutes, and then we can bring it back, and that will help us clean up this expression for the variance. All right, so this new assumption is that the variance of u given x1 is sigma squared. And we're calling this homoscedasticity, as we just kind of talked about. Or they're homoscedastic errors. So remember, what this is saying is that the variance of u doesn't depend on the level of x. So if we drew out our y and our x, remember that we have kind of this regression line here, and we have all these different points. So we have all this sample kind of scattered around. This is our sample. And so remember, I'm running out of colors, but I go back to orange here. What this is saying is the distribution of u around this line, this regression line, is the same no matter what the value of x. So let's say this is the value x a, for instance. This is the value xb. We have another distribution of u's, remember, around that regression line. And what this assumption is saying is that the spread of these points around this regression line is the same no matter what the value of x is. So you can think of this probably, kind of what I'm showing you is probably think of it in an easier way, is that can think of it as the variance of y given x is some constant. And that's kind of what I was more or less talking about here. The variance of these pink points for these different values of y, the variance of this along this y-axis is the same no matter what the level of x. That's what this assumption's kind of saying. So if the variance changed, then we're going to violate this assumption. So think about what this assumption's saying in terms of education and wages. It means someone, let's say, with a high school education, or people with high school educations have the same variance in wages as someone with a university or a master's or a PhD or trades or whatever, some other level of certification or level of schooling. And so this assumption is a really big assumption, and it's probably not going to hold in all the cases, but right now we're just going to assume it's going to hold, and we can come back and try to kind of loosen this assumption later in the course. So if the variance of u does depend on x, maybe I'll just write that so we have it down somewhere. So if the variance of u given x1 is not constant, we usually put like an I down here. So it's saying that kind of the variance of a particular level of x, particular level of, of u with a particular level of x changes. And that's why this I subscript kind of indicates it's changing, where if we don't have an I subscript, that kind of means it's constant, right? It doesn't depend on I, it doesn't depend on the level of x. So again, this is a big assumption that's probably not going to hold in many cases, but we're going to assume it's true when we're deriving the variance of our estimator. So now we can kind of go back to that derivation of the sampling distribution now. All right, so now we can think about using that assumption to simplify this expression here. So the first step we're going to do is remember that once we draw the sample, these x's aren't random. So this is kind of like a constant within this whole variance term. So remember, we're going to bring this term out and square it when we bring the variance through. So that's the first thing. So remember, once drawn, x1 is not a random variable. So we have the variance of beta hat 1 equals this first term and we have this sum here that we've taken outside of the variance, x1I minus x1 bar squared. Remember, when you take a constant outside the variance, you square it, but that's still multiplied by that variance of ui. And so the assumption we just made of homoscedasticity is that this equals some constant sigma squared. So if we're multiplying this whole sum by a constant, we can take that out of the sum. So if we take that out of the sum, we get sigma squared times, that dot is supposed to be a times, x1I minus x1 bar squared over this whole denominator here, x1I minus x1 bar squared. Remember, we squared the whole thing. Well, now that we kind of stop this multiplying of each I every time, once we've assumed this is a constant and brought it out, now we can cancel this whole term with one of those squared in the denominator, and we're left with the variance of beta hat 1 equals sigma squared over x1I minus x1 bar squared. And so one way to think about this, an alternative way to think about this, is sigma squared over the SST of x1. So the variation, the sample variation in x1. So notice that, like, the bigger the variation in x1, the smaller the variance. So we'd like a lot of values in a wide range of x1 to help us narrow down and reduce the variance of our estimator for the slope parameter. So we prefer these observations that we get in our sample to be spread apart rather than all clumped together. And remember that we can't estimate it at all if we only have one value for all of our sample for x1. All right, so we just showed that the variance of beta hat 1, after just a little bit of algebra, we found it was sigma squared over the sum of x1I minus x1 bar squared, or the total variation in x that we were just talking about. But we can't estimate this, right? Because we don't know sigma squared. We don't know, we can't calculate this yet. Don't know sigma squared. So we need to estimate. So we're going to have to estimate it. And so when we think about the estimation of sigma squared, sigma squared hat is going to be our our estimator, so that's why the hat's there, of sigma squared. And what this is going to be equal to is the sum of squared residuals. So we're going to add up all of our residuals. Well, add up the square root of all of our residuals. And instead of just having 1 over n on the outside, we're going to have n minus k minus 1. And this k is the number of x's in our regression, which equals 1 now. And so we often call this s squared instead of sigma hat squared. And that's going to be equal to the sum of ui hat squared, just rewriting that again, and just putting n minus 2. We can write it multiple ways. That's just the SSR over n minus 2. And so if we plug this back in, and we want to actually calculate the variance of beta hat 1, we put a hat on the whole variance, right? Because that's showing that we're actually calculating it using our sample. And that's going to be s squared over the sum of x1i minus x1 bar squared. Oftentimes you want to have the standard error of beta hat 1, which is just the square root of this variance. Okay, so that's the variance theoretically. We don't know what this sigma squared is, so we estimate it. Well, how do we estimate it? We're going to use our residuals. It's like a natural way of estimating it, obviously. And so we're going to sum up all of our squared residuals. And this denominator here, sometimes called a degrees of freedom correction, in that we're trying to make sure that this is a consistent estimator of the actual sigma squared. And there's kind of like a bias on that, so that's why we have to subtract 2 instead of maybe just having it over n like we did before. We're using up some information, basically, is how you can think about it. And so our estimated variance here, so our hat, is our SSR over the sample variation in x, or this expression here. Oftentimes in hypothesis testing about one parameter, we're going to be using the standard error, which is just the square root of this.